So Tim, can you see the chat?
You know, just thought I should do that. Let me see if it works.
Because the way it's been working, I mean, except for Martin's lecture, is people, I
Right.
mean, you probably saw that people type a bunch of questions in the chat and you can choose to handle them in any way you like. It often pays off to just stop and answer the question. It's usually some clarification question and stuff like that.
Yeah, no, that makes sense. I just need to figure out what I can see everybody's faces. I just need to add view, show chat. Okay, got it. Okay, chat is being shown. Yeah, I'm just juggling a few screens here, but I think it's all set up.
And if it doesn't work, we can read the questions for you or have people raise their hands or some other option.
Yeah, of course. I also have my notes on the screen, so you know there's a couple things floating around. But it seems to all be working pretty well. So
yeah, so far it looks good. And again, we should wait a couple more minutes just so people can sign in.
yeah, of course.
All right, I think we can start. So welcome to the second lecture of the second week. We're happy to have Tim Linden telling us about dark matter indirect detection. Tim is an expert on looking for dark matter by looking up, and he's going to tell us all about that in a few lectures. Again, remember, there's an extra lecture today at 3:45 TASI time, and that will be Martin's lecture on dark matter. So Tim, go ahead.
Great. Thanks so much for having me. It's too bad we're not all able to meet in person, but welcome from Stockholm, and where it is 7 p.m. and we'll be bright for another 4 hours. So I'm here to talk about dark matter indirect detection today, and I want to kind of motivate, as a very poor historical record, what some of the major observations that led to our detection of dark matter, our knowledge of dark matter as we see it today, looks like. And I say somewhat ahistorical because I'll be skipping over important contributions from various authors. I'll be biasing things in a way that I think leads to a decent narrative rather than anything that is particularly truthful to the many contributions by many different people who have worked on this topic. So let's start with our view of the galaxy, and let's do sort of a crash course in the astrophysics of our galaxy that might lead us to think that there might be something else out there. So this is a galaxy, some artist rendition of a galaxy that looks very much like ours. For some of the scales that are important here, the radius of this galaxy is about 30 kiloparsecs. That is about 90,000 light years. And the galaxy is, not spherically symmetric. It is a disk, and it has a halo height. Let's get rid of that. Has a halo height that is much smaller. It is only about 0.5 kiloparsecs. So it's a very, thin, very wide disk. Where are we in this galaxy? If this were the Milky Way, we're somewhere about here at the position of the sun. The sun's best position from the center of the galaxy is about, let's actually switch to a better color here, is about 7.8 kiloparsecs from the center of the Milky Way. And that comes with a little bit of a note, which is that it has been assumed via historical reasons, that in the particle physics literature, the sun is 8.5 kiloparsecs from the center of the galaxy. And that was set some decades ago when that was the best fit measurement. And now, in order to keep all assumptions the same and be able to compare between different works as well as possible, we typically assume, for the purposes of indirect detection studies, that the sun lies 8.5 kiloparsecs from the center of the galaxy. But note, astronomers will often use the best, most up-to-date value. How big is our galaxy? Well, it depends on what you're talking about. If you talk about the stars in the galaxy, mass of the stars here, for the Milky Way, it's about 4.6, 5.3 times 10 to the 10 m(O dot). And that is the mass of the sun, which will be always here as a circle with a dot through the middle. So about 53 billion times the mass of the sun, give or take. That is the mass of the stars and all of the luminous things we can see in the galaxy. And on top of that, there's some mass from gas. So m gas here, which is around 5 times 10 to the 9 times the mass of the sun. So about 10% as much as the mass that's actually in the stars. And there's also some density profile within our galaxy. And this is very roughly given here by rho of r, and z is the scale height, is equal to some double exponential r over r, e to the minus, let's see here, z over z, where r is around 3 kiloparsecs, and z is around 0.1 kiloparsecs. So that gives you some scale. You have some peak of density rho is then multiplied by r as we're going radially out. So if you ask where the average star is in our galaxy, it's around 4 or 5 kiloparsecs from the center of the galaxy. The sun is, within 1 standard deviation from where the most probable location of a star is, not anywhere special, and the galaxy goes out to a much, much larger distance. So let's take that and let's just try to do very, very simple, classical mechanics. Let's start with F equals ma, or some version of this based on gravitational attraction, that gmm over r squared. And let's assume that the stars are moving mostly in circular orbits around the center of the galaxy, inside the galactic plane, because that's what they're doing. So this is going to be mv squared over r. And that tells us that you can solve this for the velocity. And by solving this for the velocity, you can actually do something very interesting. You can weigh the Milky Way, which I will often just put as MW. So you calculate the velocity, just rearrange some stuff, and this is equal to GM over R after these mass terms here drop out. So what does this look like? You could make some plot and then of what this is supposed to look like for a galaxy, and then you could compare that with observations. So here we have the radius in kiloparsecs from the center of the galaxy to some given star that we're going to observe. And we have the velocity of that star. And, if everything was just a point object, all of the mass in the galaxy was, right at the center, you would have something that looked like this, V for a point object. But actually, the mass of the galaxy follows those density relationships we just looked at. So you actually see something, that looks a little bit more like this, where it's rising, and then it flattens out over time. So this is from some density distribution that is rho of r is proportional to e to the minus r over r, and then has some z dependence that doesn't really matter for the purposes of this talk. So that's what we expect, and astronomers like to look at stars, so they go out in the at night and they do that, and they see how fast our star is moving, and they look at a different galaxy. It's actually very hard to look at the Milky Way and calculate this because we're inside the Milky Way. And so, very small differences in the distances to various stars and things make a huge difference in your calculations and lead to there being a large error. So what they actually did was look out at the galaxy M31, which is also known as Andromeda, which I can't spell. So Andromeda is a neighbor galaxy. It's the closest Milky Way-like galaxy, and so it's the typical Milky Way analog galaxy. So this was first done by Vera Rubin and Ford in 1970. There were also measurements of velocity distributions in galaxies by Zwicky and others in the 30s. That's where I said this is not a very historical overview of the topic. For historical overviews, I'll point people to the Dark Matter History by Gianfranco Bertone and Hooper, and also for a more in the moment history of kind of the decade before, a paper by Sandy Faber and Jay Gallagher down here. Okay, so Rubin and Ford look out at the M31 galaxy. They look at stars that are rotating. They're astronomers, so they plot this in angular coordinates. But up here, for physicists among us, they give us the distance in kiloparsecs from the center of the galaxy to the stars that they're looking at. And they expect something that looks slightly more complicated than what I showed before. They expect some big bulge of stars in the center to have a lot of mass. And then they expect, something that looks like this, where the disk contribution is supposed to go down as a function of time, or maybe go up slightly and fall down, something like that. And what they instead see is that as you go very far from the center of the galaxy here, 10, 20 kiloparsecs, you get a totally flat distribution of velocities. The stars are not moving slowly at the outskirts of galaxies like you expect. And this is maybe a little bit clearer on a more recent plot. This is also of M31, but with up-to-date or at least 14-year-old observations. So going out now to 35 or 40 kiloparsecs from the center of the galaxy, they get this contribution here from the bulge in the center of the galaxy. they get a contribution from the stellar disk, which actually is just going down a little bit in these coordinates. And you get a totally flat mass distribution, and you can infer the additional mass that you need to make that mass distribution, and it's this halo term that looks like this in the plot. So they calculate some mass estimates of these different components by measuring this rotation curve. And for M31, they get that the mass of the stars at a radius of less than 35 kiloparsecs, because you care about the mass that's constrained within this region, is about 10 to the 11 solar masses. The mass of this new dark matter component at the same R is less than 35 kiloparsecs, is around 2 times as much, 2 times 10 to the 11 solar masses. And there's something that you should note, that this is the mass confined in a small region, because that's what makes the rotation velocity. This is much smaller than the mass of the galaxy itself, which is usually determined by this R virial radius, which for a galaxy like this is around 700 kiloparsecs or so. And that is equal to around 2 times 10 to the 12 solar masses. And I think there is something in the chat. Yeah, so M star is the mass of stars. So it's anything that is luminous and can be seen, which is mostly stars, and the average star looks a lot like our sun in terms of the mass contribution, or something that's maybe about half the mass of the sun. Good. So what do you do with this? You have some density profile. We can just turn this equation that we had before on its side. If V equals G M of R over R, and we want to assume, or we observed, I guess, let's say that we observed that V is constant. Then we know M of R is proportional to R. And if M of R is proportional to R, you can calculate this out. M of R, 0 to R of rho of R prime, R prime squared, dr prime, tells you that rho of R is proportional to R to the minus 2. And you can compare that with the baryons, which we just calculated, which said that they look something like proportional to e to the minus R over R, e to the minus C over Z. And these are very different distributions, and they go out to very different radii. We saw that the dark matter component continued to be very important at 35 or 40 kiloparsecs in M31. So just from this observation of galaxies and rotation curves, we know that dark matter has a large density. And also, we know that that distribution differs from stars. Right, so it is something new that we have to deal with. So what are some of the implications of this? Just looking at this observation of stars moving around a galaxy, where the galaxy is something very similar to the Milky Way, chosen to be so. So the first implication is for the dark matter velocity distribution. So if the mass, and these are numbers we're just gonna, that are gonna come up multiple times in this lecture, just because I'm picking the same template galaxy and calculating averages at the order of magnitude level time and time again. So the mass that is confined within 35 kiloparsecs of stars and dark matter was around 3 times 10 to the 11 solar masses. And then the velocity that you can calculate, circular velocity is equal to square root of gm over r. The escape velocity, the velocity at which some test particle would fly out of the galaxy never to return again, you can calculate. This is the rocket equation from classical mechanics. It's just 2gm over r. And that is equal to, you can plug some figures in here, 2, I guess we'll keep that. And then g in astronomers' units Why am I taking 35 kiloparsecs? Great question. That is because when we went back here, this is what Carnegie et al. Calculated. And so that is their stars go out here to about 35 kiloparsecs. And so I'm just picking that as a number where we have some sort of observations and where dark matter is relatively important. Other than that, absolutely no reason. It's a good question because I'll choose 35 kiloparsecs for the rest of this lecture for the same, absolutely no reason. So G in astronomers' units is 4 times 10 to the minus 6 kiloparsecs per solar mass, and kilometers per second squared. So these are silly units, but they allow us to get something relatively reasonable at the end. And the mass of this galaxy is 3 times 10 to the 11. And if R is 35 kiloparsecs, this tells us that the escape velocity here at this radius, of course, this is a radially dependent statement, is around 260 kilometers per second, which is around 10 to the minus 3 times the speed of light. So dark matter in galaxies, at least, you know, maybe there's some other dark matter somewhere else in the universe, but the dark matter that's in the galaxies and controls the rotation of the galaxies must be moving slowly. Now, whether you call this a cold dark matter or warm dark matter, people tend to refer to what the dark matter velocity was at the time that dark matter decoupled and formed structure. But this is an indication that at least now, whatever forms the dark matter is cold dark matter, is something that's moving slowly. I think Martin will give some more insight later into, you know, whether dark matter is truly cold at the point of freeze out, or whether there's some warm dark matter component or something like that. The other thing that's important, right, is that the dark matter that's in our galaxy didn't show up yesterday. It was important in forming the galaxy, 13 billion years ago. And in the early formation time, you can try to calculate what is the velocity distribution of dark matter that gives you the right, galaxy today, and put stronger and stronger limits on its velocity distribution earlier in the universe. So that's the first implication. The second implication, Martin, I'm going to steal this from Martin, who said he would show it in lecture 3, but I'm going to preempt that and show it now, is that you can calculate from this the minimum mass of a fermionic dark matter component via the Pauli exclusionary principle. This is also in this form also often called the Tremaine gunbound, and refers to their paper from 1979. And the idea is simply this: any fermionic particle can only fill, so many states. And I think this was mentioned in the last lecture as well. The maximum filling of any state of some position space and some momentum space is equal to mu. Mu was taken in the last lecture to be an order 1 number. The same is true here. It technically depends on the quantum numbers. So if you have spin, if you have color, if you have something else, you can make this, a number that is slightly larger than 1 for, maybe order 10 for some quarks or something like that, but nothing crazy. And so the total number of particles in our galaxy, or Andromeda, is equal to n chi. And this has to be less, because of exclusion, as some integral from 0 to the maximum momentum you can have of all of the different momentum spaces you have. This depends on the dimensionality of the problem. And then times this filling ratio. So this is equal, you can calculate this out, to mu p max to the 3rd power. But we looked at the galaxy and we know what p max is for the dark matter particles that are in the galaxy, right? So p max is equal to m chi times the escape velocity of the dark matter particles that are in your galaxy. The ones that escaped don't exist anymore or don't help you. So NV escape is around 10 to the minus 3c. So, you know, to calculate this out, you get m chi to the third power via escape to the third power, that's your momentum, is greater than or equal to the number of dark matter particles that exist. And just taking those numbers, I said we're just picking these same numbers over and over again for no reason. This is 2 times 10 to the 11, 2 now because I'm just considering the dark matter mass. And this is for pi 35 kiloparsecs to the third, and the dark matter mass goes down there. And so you can calculate this out, and well, we'll just throw in some unit conversions that I guess they're worth knowing. I don't know. Now, in the days of Google, they're probably not worth it knowing. 2 times 10 to the 11 solar masses. I'm just going to call this V to save myself some writing. There are 10 to the 66 EV in a solar mass. And 1 EV is 2.5 times 10 to the minus 25 inverse kiloparsecs. Okay. And that gives you that the mass of the dark matter particle is greater than 12 EV. And I don't know why I kept the second digit there. So that tells you, I'm going to go over what we did. You start with, you know, you can only have one dark matter particle per state because of the Pauli exclusionary principle. How massive do the dark matter particles have to be so that they add up to 2 times 10 to the 11 solar masses within 35 kiloparsecs of radius? And you find that they have to be at least, you know, 10 EV or something like that. The current constraint on this is actually better, and it comes from dwarf galaxies, which we're just about to talk about. And they get something around m chi greater than around 100 EV, just by looking at better galaxies and picking better numbers than 35 parsecs. For the spatial variable, good. F is just the state. You know, it depends on the particle physics of the dark matter. If dark matter has color, then maybe F is some larger number. If it's you know, particles and antiparticle pairs that are both spin 1/2, then it's 4 or something like that. So you can you know, pick this based on your particle model, but then it's going to create order 1 changes in this value. And for why the spatial variable x disappear, it's here in this volume calculation because I'm calculating out the volume here. And I'm assuming something, which is that my dark matter, you know, another thing that's wrong with this kind of order of magnitude calculation is I'm assuming that my dark matter density is just flat over the entire galaxy, and that's what fits the rotation curve correctly. Good. Okay. So let's go to dwarf spheroidal galaxies. They seem to be important, as I just mentioned from this more recent paper. And I apologize to people who it is currently about their lunchtime or about their dinner time or something like that. This is a extraordinarily accurate cake of where dwarf galaxies are surrounding the Milky Way with a gamma ray map in the background. So this is the plane of our galaxy here, which is red sprinkles. These are the Fermi bubbles above and below the galactic plane. And then above and below the plane, you see these little fish. And these fish, the green ones are dwarfs that were observed prior to 2013, 14, something like that. And then the dark energy survey dwarfs here, of which this cake was in celebration for, are the orange sprinkles at the bottom of this. And so there are these different dark matter structures that have been observed around our galaxy. That's what this is supposed to say. The Fermi bubbles are something that will probably, it's a bunch of extra high energy emission from astrophysics. It's not important for this talk, but it showed up in the cake. It was important for the context of the cake. Good. So what does an actual dwarf galaxy look like? Here is a particularly massive and well-studied one called Fornax. And you can see it, again, by looking at stars. So, you know, this is a picture taken with some telescope, and you see some huge overdensity here where there are a lot more stars than you would have naively expected in that part of the sky. You can compare it to the stellar density, say over here, for instance, and notice that there's a large overabundance. You can then do more, you know, detailed simulations. You can find out that all of these stars are about the same distance away, that they're all moving with about the same velocity, and you determine eventually that they are orbiting around some common center around here somewhere. They're all orbiting this with some relatively small velocity. So Fornax has thousands, tens of thousands of stars. What's actually most interesting for fundamental studies of dark matter are the smallest dwarf galaxies that exist, which I didn't show here because they're very hard to pick out by eye compared to the background. They have to be seen statistically. But some of them, for example, Segway 2. There are now, I should mention, about 60-ish dwarf galaxies around the Milky Way. And that's a number that's increasing rapidly and will continue to increase, especially with the LSST coming online here in the next few years. Anyway, Segway 2, it has a very small total luminosity. So L star is the total luminosity of all of the stars in this thing, and it's about 860 times the luminosity of the sun. So it's, you know, you stack about 860 suns. Better, I think you stack about 1,000 things that are mostly smaller than the sun, but some are entering giant phases and are thus brighter. So, you know, some distribution of stars with different luminosities, about 860 times the luminosity of the sun. You can calculate by knowing how big all of those stars are based on their temperature and radius and all these sorts of things, that the total mass of all the stars in this is about 840 times the mass of the sun. So there's a very small mass that is produced by the stars in this. But everything is orbiting around some common center in this galaxy. The rotation velocity that you calculate for all the stars that are orbiting is around 10 kilometers per second. It's much smaller than the 200 kilometers per second or so we calculated for the Milky Way. And this is at a radius of around 30 parsecs now, instead of 30 kiloparsecs, so a much smaller radius. And this gives us a dynamical mass for this system that is around 5 times 10 to the 5 solar masses, compared to the 840 solar masses that are seen in stars. So you get a what we call a mass to light ratio, which is one of the more interesting measurements you can do here. The mass dynamical, it's dynamical mass, divided by the luminosity of the system is around 560. For comparison, in the Milky Way, the total mass of the Milky Way is around 10 to the 12 solar masses. Sorry, this is a little small to see. And it's about 2 times 10 to the 10 solar luminosities. So it's around 50 in the Milky Way, which tells you about how dominant the system is. So dwarf galaxies are extremely dark matter dominated. How do you find the mass in stars? Great question. You look at the temperature of the star, you can pick up spectroscopically. The luminosity of the star, you can also pick up optically. So you calculate the temperature and the luminosity, which tells you now how big the star is, so you get its radius. And then there are relationships that are known from catalogs of stellar evolution between the radius of a black body star, its temperature, and that gives you the mass of the various stars that you're looking at. And then you add the masses of all of the stars that you have seen. Now in galaxies, that's a good point because it's a little bit tricky. You see in a galaxy like Segway 2, you don't see 800 stars. You see about 10 or 20 stars that happen to be particularly bright because they are evolving off the main stellar sequence. Remember, when the sun is kind of ending its life, people say like the Earth will be inside the radius of the sun. People say that because it's true. You see those stars because they're particularly brighter at that time. And then you use the evolution of those stars to calculate how many are going off at different times and becoming particularly bright, and how many underlying stars there must be for the total luminosity. The other way you can do this is you can just try to integrate all of the luminosity that's in this whole region of the galaxy and try to get the total luminosity of it that way. Those measurements match pretty well. Okay, there are some more questions here. Why does dark matter dominate dwarf galaxies much more than, say, in the Milky Way? Great question. To some extent, that's open research. The common idea is as follows, and it has to do with this escape velocity being very small. So what we think happens is very early on. So dark matter is forming. Dark matter, you'll see this in the cosmology lectures probably most clearly. Because dark matter has more total mass than the baryonic matter, the baryons tend to follow the dark matter. So where the dark matter is, that's where baryonic matter, protons and electrons tend to congregate and eventually form things like stars. So what we think is a combination of, baryons tend to follow larger dark matter structures better. The second thing is, because this escape velocity is only about 10 kilometers per second, once the first supernova goes off and ejects a lot of energy, a lot of power, that tends to push away all of the gas and the stars in very small galaxies and just kills all of the star formation that was going to happen afterwards. Dark matter, interestingly, and these are good limits on, say, does dark matter interact with electromagnetic fields? Dark matter seems not to be highly disturbed by having supernova go off nearby. And so the dark matter still seems to be there, but the stars aren't being formed anymore. What is dynamical mass? Dynamical mass is the mass that causes anything to orbit around it. So, that is my GM over R. This is a dynamical mass, that I said is proportional to V squared. Something like that. So that has to do with the mass we can measure from rotation curves, and then the mass, we can calculate from the rotations of stars. This is maybe a spectroscopic mass or something like that, is how an astronomer might call it. Why do we compare the dynamical mass for a dwarf galaxy to L's sun, but not for the Milky Way? We could do it for the Milky Way. It's most interesting for dwarf galaxies because these numbers are significantly larger. I also noticed that I wrote this backwards, and the actual value is like 650 and not 560. Anyway, should be L star in the oh yeah, sorry, L sun. Yes, thank you. That would have answered that question better. That should be L star down here. Thanks, Shane. Okay. So what are the implications of looking at this object? We already said that for the fermionic dark matter, this actually sets the strongest bound. Why does it set the strongest bound? Let's think back to that calculation we just did. The first thing is that the velocity distribution is only 10 kilometers per second, which means the maximum momentum that I integrated to will be smaller. The second is that this is a smaller radius. On the other hand, it's also a much smaller mass, but it turns out you deal with all those factors at the same time, and you get a slightly better bound. Okay, what else can you do? What is now the minimum mass of bosonic dark matter? This is that 10 to the minus 22 EV that was mentioned in Martin's talk, and I'm just gonna scoop that as well. So this comes from the de Broglie wavelength, and it's a rather conceptual calculation, right? The idea is just that if this object, our dwarf galaxy, is 30 parsecs, then my dark matter better not have a wavelength that is larger than 30 parsecs. So my wavelength is equal to Planck's constant over the momentum of the particle. And so at 30 parsecs is approximately 10 to the 26, that is not in the exponent anymore, 10 to the 26 microns. And 10 to, so this radius here, that's the wavelength I want to care about, 10 to the 26 micrometers compared to Planck's constant, 1.2 eV micrometers divided by the momentum of the particle. That tells me that the minimum momentum is around 10 to the minus 26 electron volts. And we just calculated, or we observed, that the escape velocity from the dwarf galaxy is also on order of 10 kilometers per second or something like that. It's 2 times the rotation velocity. So this is going to be the mass of my dark matter particle chi times 10 kilometers per second over c. And so the minimum mass from this really rough calculation is around 3 times 10 to the minus 22 electron volts. You can do this in an updated way. You can take into account the actual, radial distribution of where the dark matter is by looking at the different rotation velocities of all the stars, et cetera, et cetera. They actually get a slightly less good bound than the one that I roughly calculated here, 4 to 6 times 10 to the minus 22 eV. So if your dark matter is less massive than that, it will be too poorly localized to produce the rotation velocities that are seen in the very smallest galaxies. And this is going to be the best constraint because this is the smallest dark matter dominated system we can see. The second implication is almost as straightforward, actually maybe even more straightforward. The maximum mass of the dark matter particle can also be calculated here. This is the very hard conceptual idea that dark matter can't be heavier than the dwarf galaxy. And so again, I guess the theme of this talk is moving between astronomy units and particle physics units. 2 times 10 to the 5, I think I calculated 2 times 10 to the 5 here because there's an even smaller dwarf, is around 10 to the 71 eV. So whatever your dark matter is, it can't be larger than 10 to the 71 eV, or maybe that's not a very useful unit. It can't be larger than about 200,000 times the mass of the sun. And you can do a bit better once you put in a specific model. Martin mentioned, and again, stealing from him, that anything that's larger than the Planck mass is going to be some sort of composite particle. And so it depends on what your composite your models look like. So for example, if you say that this is a bunch of primordial black holes, then you can deal with the fact that it can't be one primordial black hole because that would be right in the center. And our measurements of the different velocities of the different stars at different radii tell us that all the dark matter isn't just a point particle at the center. So you need some, maybe around 100 different primordial black holes to get the velocity distributions right of the different stars that you see. So then, M chi for the primordial black holes is less than around 10 to the 69 eV or something like that. I guess you could produce some sort of, axion condensate or something like that acts as one condensed system, or some sort of, condensed composite particle that has the right radial distribution of the dark matter. And then you couldn't do much better than your 10 to the 71 eV max. So getting back now to a slide that Martin stole from me, you can put this on the same, we all stole from somebody who did this 40 years ago. You can get the different mass constraints on dark matter. So, but these are important numbers to remember. So I'm going to write them down again. 10 to the minus 22 EV for bosonic dark matter, around 100 EV for fermionic dark matter. I think Martin gave 1 keV as the number. That's also, relatively reasonable. Notably, the Tremaine gunbound from their paper assumes a thermal freeze-out model, and then it obtains a constraint that is about 1 keV. So that's commonly quoted in the literature as well for that reason. If you don't assume that the thermal freeze-out mechanism that Martin will talk about later this afternoon, then you can get down to about 100 EV. The Planck mass is up here at about 10 to the 28 EV. And then the maximum mass of any dark matter particle is around 10 to the 71 eV. So this stuff over here has to be some sort of composite. This sort of thing over here has to be some sort of boson so that I can fit infinitely many particles in the same state because they're all so light. And then in this region, I can be either a fermion or boson. Great. Okay. So now let's get into a little bit more of just kind of the details, some things that are useful to know when looking for dark matter out in the galaxy and universe above us. The most important number that you should have in mind is what is the local dark matter density. And the most important way to remember the dark matter density is that it is 1 squirrel of dark matter per Earth. The dark matter density around the solar position is about 1 squirrel within the radius of the Earth. And of course, the question is we need to find this squirrel. So more numerically, and in less of an XKCD way, what is the local dark matter density and how do we measure that? The local dark matter density in more normal particle, let's say more boring units, is around 0.01 times the mass of the sun per parsecs cubed. And note that this is a really small number and this is challenging, right? The mass of the sun is about 1 solar mass, and Alpha Centauri, the nearest next star, is around 1.5 parsecs away, which is a combination to tell you that the mass of dark matter right next to us is very small, not only in terms of inside the Earth, where it is a ratio of a small mammal to the size of the Earth, but also in terms of our very local region of the galaxy, it's much smaller than the baryonic matter density. And so determining from some sort of dynamical standpoint what the dark matter distribution looks like is a really challenging topic. You can see this historically here on this plot on the right by Justin Reed has a really nice review talk on this. There's actually been quite a bit of new observations after that talk, particularly based on Gaia data, but that's a nice review of the different techniques that exist. And this plot is from that. So they give you a best fit here at about 0.008 solar masses per parsec. And then on the right, this number here in physics units is equal to 0.3 GeV per cubic centimeter is another number that's worth noting. So there are several methods that are used to do this. The first is from galactic rotation curves. The same way we did this at 35 kiloparsecs, you can do this here and just look at, very carefully count the number of baryons that exist near our solar position and try to look for some sort of excess. You can also, a much more powerful method is look for local stellar kinematics. And you take advantage of the fact that the galaxy is a very thin disk. That's a very poor illustration of a thin disk. And the dark matter, there's very little dark matter inside the disk, but there's dark matter up here and below here. So as a star might have some peculiar velocity with respect to the disk, and so most stars are orbiting above and below the galactic plane, and how far they go above and below the galactic plane depends on the mass distribution that they're seeing as they go up and down below the plane. So if you calculate the velocities of stars, their z velocity with respect to the plane perpendicular, you can get some sort of calculation of the distribution or the total mass of the dark matter component and separate it from baryons. But there's a very important point I think everybody should be cognizant of because you will spend the rest of your career forgetting this and then having arguments that were not worth having, is that along with the uncertainty in the radius of the sun, we said that the radius of the sun, particle physicists say is 8.5 kiloparsecs, astronomers say 7.8 kiloparsecs. And then there's a big shaded region here in the local dark matter density. Along with our sun, this produces a factor of 5 uncertainty. In any constraint on dark matter annihilation in the Milky Way. So, you know, if somebody tells you, oh, we finally did it, we looked at the center of the galaxy and we decided the dark matter annihilation rate, we'll get to the numbers later, is less than 3 times 10 to the minus 26 at this mass, and so this model is excluded. You need to remember you should move all of those numbers by a factor of at least 2 up, maybe a factor of 3 up, a factor of 2 down, something like that. And that's what you're actually constraining. And until we do the dynamics better, that's the best we're going to be able to do. Similarly, if you're comparing 2 measurements at different locations to each other and they don't agree, you need to remember there's a huge fudge factor dealing with our uncertainties and how much dark matter there actually is near our position in the galaxy. Okay. Now, just to get into a little bit more of the history and a little bit more of matching observations and doing simulations, what are some of the dark matter density profiles that are actually used and actually fit all of the data we see? So normally, you know, for the purposes of this talk right now, I've assumed a totally constant dark matter density or something that is just 1 over r squared from the calculation of rotation curves at long distances. In the dwarfs, I didn't really care about the density, but you know, when you do say simulations of dark matter particles, or you look at stars at lots of different radii, you get things that fit the data. The most famous is the Navarro-Frank-White profile. Navarro, Frank, and White, named after its 3 authors. There's a very good picture that people should use in these talks, although I didn't, of Navarro, Frank, and White standing in profile and having their picture taken. So the Navarro-Frank-White profile tells you that rho of r, the dark matter density, is equal to some normalization factor. And then it is r, the distance from the center of the galaxy to where you are in some spherically symmetric fashion, over some scaling radius to the minus 1 power. And then another term that looks as 1 over r plus r over the scaling radius to the minus 2 power. And so what that looks like is something where the radius is here, the dark matter density is here, and then the density starts as falling as r to the minus 1 because it's small radii that are smaller than this scaling radius. This term is basically constant, and then eventually falls as r to the minus 3 once you get, you know, well outside the scaling radius. The transitions here at r scale. And for a galaxy like the Milky Way, the scaling radius is around 20 kiloparsecs. That's the best fit to the data. There's something else you'll see in the literature, and you should be warned about. I'll call it the Generalized Nfw Profile. Many people will just call this the NFW profile, so you have to be careful as to what people are actually naming things. And this is rho of r equals some rho 0, and then r to the r of the scaling radius to the minus alpha power, and then 1 plus r over the scaling radius to the minus 3 plus alpha power. This is the same profile in general, except, you know, it goes as r to the minus alpha here, where alpha is some number you fit to the data, and then it still goes as r to the minus 3 at some larger radii, and it breaks to the same number. Some questions popped up. Profile is generalized from dark matter plus baryonic matter simulations or dark matter only. Great question, and it depends on the data set you're talking about and which simulation is done. You know, more and more, the best state-of-the-art simulations are including the effects of baryons. Right now, it is thought that, you know, into the solar position and maybe slightly in closer to the galaxy, the baryons don't influence the dark matter distribution that much. There is a hotly debated topic about what baryons do to the dark matter profiles near the centers of dwarf spheroidal galaxies, and also what they do very close to the center of the Milky Way galaxy. And we'll see that a little bit on the next slide as well. Do they come from theoretical considerations, or is it mainly fitting to data? Analytic fits to data for the first NFW profile, and then top-down models of basically multi-particle n-body simulations are the state of the art right now. So you build a universe or a galaxy or a cluster of lots of galaxies. You start them from the initial conditions of the universe, which you get from the cosmic microwave background. So you start them from a couple 100,000 years old. And you start with the linear power spectrum. You'll learn about this more in the cosmology section of the initial fluctuations of our universe at a couple 100,000 years. And then you just let the n-body simulations interact via only gravity, because we think dark matter, forms its structure via only gravity. And then you get some profile out from what the universe looks like today. The regions that start with small overdensities get bigger and bigger overdensities and eventually become galaxies or clusters of galaxies. The things that start with small densities, the density, gets more underdensities, or the densities don't get any larger. What is the form of the NFW profile? Just by looking at data. Okay, I think I mostly answered that. It's a similar question. Is this related to MOND? Good. So I'm not addressing MOND so much in these talks. It's maybe worth bringing up in response to a question, right? So MOND says that there is no extra mass in the galaxy. And so what they do, if we had V, let's see here. I can, let's see if this breaks everything. I can just add another slide here. If V equals the square root of GM of R over R, what I did was I took this term and I modified it with dark matter. And what they do, we said that this is around constant before. That's the observation that you can't get away with. What MOND does is it takes G and sends it to some effective G of R, where, now this, the gravitational constant, the force between two objects is not the normal 1 over R squared relationship. So MOND, can be produced to fit the observations of galaxies and the rotation curves of many galaxies. There's not a good reason for the exact number of the new change in acceleration that you need in MOND parameters. It has a very hard time matching things like the cosmic microwave background or the formation of large-scale structure early in the galaxy, things like baryon acoustic oscillations. There's a lot of things that you'll learn about in more detail in the cosmology lecture that are hard to fit with a MOND model. And I think why, well, a topic of research, it's not the kind of most interesting topic of research today. That's maybe my own bias. Can you explain again where the uncertainty in the local dark matter density for dark matter annihilation results again? Sure. I think we're doing better with Gaia data, and we're going to do even better over the next few years when Gaia's next data release comes out. I think called Data Release 3 or something like that. And this is worth mentioning because this is a crossover topic that a lot of particle theorist-oriented people are very interested in, even though it's astronomy. It's very astronomy-oriented as a field. So this is going to get smaller. And so the uncertainty comes from this error bar here, this error band of these different observations. This is better actually down here zoomed in, right? So consistent with current observations is about 0.2 GeV per cubic centimeter, and then a maximum of about 0.58 GeV per cubic centimeter. What we'll see in a little bit is for particle physics models like thermal WIMPs, they tell you what the cross-section for dark matter would be. And then to get to how bright the indirect detection signal is that you'd want to see, you have to multiply by the dark matter density that's there. And in fact, you have to multiply by the dark matter density squared because I need two particles to come find each other. And so that's a very large ratio between those two values. Do I need a cutoff radius for an NFW profile? Or yes, the mass in a great question. Yes, they choose a cutoff radius at a point for totally odd historical reasons called R200. I'm not going to go into the details, but it is when the density from the galaxy, the dark matter density, is divided by the average dark matter density over the entire universe. Rho average is equal to 200. So once the dark matter, once the galaxy is contributing less than 0.5% of the total density of dark matter that should exist compared to the total average dark matter density in the universe, they cut the NFW profile off at that point. Do dark matter profiles predict results in MOND? So, I mean, I think you can change these parameters like RS to get different fits to the data. So like if you had a different rotation curve, you could change the scaling radii to get different values. And so MOND, in some sense, if your only evidence was galaxies, I think MOND would be a pretty reasonable model for the data. My theoretical prejudice comes not from maybe the observations that I've talked about thus far, but from all of the observations of cosmic microwave background and other things like that that are very hard to explain within Mondian models. But for galaxies, you're right. The self-similarity in MOND models between the baryonic density, what's called the baryonic Tully-Fisher relationship, the baryonic density that's observed in galaxies and the rotation curves of those galaxies is very strong. And since you're not directly observing the dark matter, you get a little bit more latitude to, affect the results to fit, random data sets than you do in MOND. We're actually going to talk about the Boole cluster in just a minute, and that will maybe get on the MOND topic a little bit more. So in addition to the generalized NFW profile, there are a couple of different profiles that are also useful. The Inassto profile from Inassto, I can't remember his first name, is rho of r is equal to some rho 0 times some exponential minus 2 over some value of alpha, which you fit to the data, times r over rs. That's scaling radius to that alpha minus 1. That is a handful of brackets. Alpha here is very constrained for a Milky Way-like galaxy to be about 0.17, and RS, I think it's also around 20 randomly, but don't quote me on that. So this is actually first Inassto wrote this down to fit density profiles of luminous objects in galaxies with different values of alpha. And then it turns out this fits fairly well dark matter density profiles as well. And the last one is a profile by Burkert. This one has a different phenomenology. I'm going to show a better plot of these in just a second where this is going to become clear. Rho 0, 1 plus r over, I'm going to call this now a core radius because it actually does lead to a core. I'm going to erase this so that I can fit this in. Times 1 plus r over a core radius squared to the minus 1. Now this has a very different phenomenology near the center of the galaxy. Once you get to smaller than this value of our core, everything is just basically constant in this problem. So here our core is not like 20 kiloparsecs. It's on a Milky Way like galaxy 2 to 3 kiloparsecs, closer than the solar position. So here's what these look like. Oop, that's the slide I just made up. Here's what these look like in practice. This is the dark matter density in a Milky Way-like galaxy. So this is observations for, say, the Milky Way. This is the radius in kiloparsecs, now on a log scale. We are here. Particle physicists made this, so this is at 8.5 kiloparsecs, like I said, as we normally assume. So here, this is being fit to some local density. So remember, factor of 4 uncertainty there. Out here, dark matter is dominant. Right, we were measuring the rotation curves of galaxies like Andromeda, or we can do the same thing with stars on the outskirts of the Milky Way. And so because most of the mass density is actually from the dark matter, once you get out farther here, that has to be a very constrained number. So all of these things have to be about the same. But in here, there's some huge uncertainty. And it's very hard to measure this because the baryons are so dominant. So most of the dynamical mass of the galaxy is due to stars. And so all of these different observations can reasonably fit data sets. And note, when you get into say, this is 1 parsec from the center of the galaxy, so roughly, as close as the nearest star to us, you can have a change in 10 to the 4
in the dark matter density without really affecting the results of any observable. And that would lead to a factor of 10 to the 8 change in the dark matter annihilation rate because it goes as rho squared. That is exactly right. So the question was, is a dark matter, for indirect detection constraints on dark matter, a profile like Moore or Inassto profiles will produce more stringent constraints than one like Berg. Yeah, and that is true by a factor of 10 to the 3 or something like that for observations of the center of the galaxy, the center of the Milky Way in particular. We'll see the uncertainty is actually not so bad in dwarf galaxies. But for the Milky Way galactic center, it's a huge uncertainty. Okay, so let's look at some more astrophysical constraints. This is an observation of the Bullet cluster. This picture, I'm sure you've seen before. But let's talk for a second about what this is actually a picture of, because it's, you know, actually an amalgamation of like a picture and then a data set that isn't even actually anything you would consider an image, and then placed on top of a false background taken at an entirely different wavelength. So the background is just stars taken by Hubble. It has nothing to do with the rest of the picture. In the center, this part here that is in pink, this is X-ray emitting gas. So it is hot gas. To emit X-rays, gas has to have a temperature, T gas, of around 10 to the 6 Kelvin. And then it emits an X-rays. And so these observations are taken with the Chandra X-ray telescope. Don't quote me on it actually not being some other X-ray telescope like Rosetta or something like that. Andre just sent us all an email. Then this blue or purple region on the sides over here and over here, this is not actually an image at all. These are gravitational lensing maps. And gravitational lensing maps are used to tell us, you know, in some statistical method, where the mass from this galaxy is. So what is the Bullet cluster and what are we looking at? We saw, I'm gonna add another plot again. Okay, so what are we looking at? We're looking at 2 different clusters of galaxies. One here and one here. And they're moving at each other with some large relative velocity. And when we say clusters of galaxies, we're not talking about individual galaxies like the Milky Way or Andromeda. There are a lot of different galaxies inside of both of these things, hundreds to thousands. And they have moved and they have collided, and now delta T 100 million years, something has happened. Now these galaxies have passed. And if nothing interacted with anything, the picture would just be reversed. But what happened was all of these galaxies had gas. And gas is collisional. So it clumps up in the center. Gas moving in one direction hits gas moving in the other direction. It stops and it heats up. And it produces a bunch of thermal energy. So that's our hot gas. And but the mass observations tell us the mass came over here and over here. So the mass did pass through, but the hot gas in the center did not pass through. So that means the dark matter, and this is a very strong constraint, for instance, on MOND models. It's very hard to fit in MOND because it's easy to understand in MOND that, you know, maybe Newton's constant isn't quite constant. It depends on radius and the stars are just doing something different. But it's very hard to understand why the mass is here and the stars are over here, and they are not actually localized in the same position. So this is a strong constraint on Mondian models, and then people working on MOND have you know, tried to make models to come up and explain this, but it's not necessarily the most trivial calculation to explain. Another exercise for home. Where are the stars? Are they here? Or are they over here? Okay. So side note, what is I thought stars are kinematically like dark matter. Yes, somebody has answered it in the chat. Good. The stars are there, but the gas, remember we said before, mass of stars in an Andromeda-like galaxy was, what did we say, 5 times 10 to the 10 m sun. And the mass of the gas from that very first slide was around 5 times 10 to the 9 m sun. So this is the gas that's here. And that's it becomes very bright because a bunch of it smashed into other gas and heated up pretty efficiently. And so that's creating the observation. So let's think about gravitational lensing. And I realize I'm also getting very close to being out of time. So what is gravitational lensing? I have some background galaxy here. And I have some distribution. I have some distribution of mass here. And my galaxy emits photons. And it is bent, because of general relativity, around that mass. And so then I look out with my very expertly drawn telescope here, and I see, you know, light from the same galaxy coming from this way and coming from that way. And I get something that looks like these pictures on the bottom left. This is strong lensing, usually produced by black holes with a galaxy right behind the center of it. This is weak lensing, which is more important for our dark matter studies. And this is where, you know, none of these things is forming a perfect ring that looks like the picture, but there's some preferential rotation. You know, this galaxy is stretched in this direction, this one's stretched, this one's stretched, this galaxy is stretched, this one's stretched. And it tells you that there's some mass in this region here. Don't we expect some offset between stars and dark matter? Yeah, potentially, and that's kind of an active field in determining exactly what the constraint is on dark matter from bullet cluster observations. So let's try to calculate that actual limit. We have some cross-section, which is equal to sigma times the dark matter density, so mean free path, sorry, which is equal to the cross-section times the dark matter density. And the dark matter density depends on the dark matter mass density. So it is equal to sigma times rho over m chi. And so just for our illustration, we're going to assume that this collision was 2 galaxies, 10 to the 14 solar masses, 2 galaxy clusters, so they're much bigger than galaxies. And we're going to assume the radius of each of our colliding galaxy clusters is the same, and it's 100 kiloparsecs. I'm just making these numbers up. In this case, sigma is less than m chi over rho. And remember, so what is going to happen is a dark matter particle from one galaxy cluster has to go through the entirety of the other galaxy. So it's the 2-dimensional. I don't care about the dimension of, you know, how long it takes. What does it hit a dark matter particle at the beginning or the end of this galaxy? The galaxy looks like a disk to the particle coming through. So this is m chi over the mass of galaxy A, if I'm talking about a particle in galaxy B, divided by pi r a squared. And so that is m chi over, this happens to be 2 times 10 to the 47 grams is what 10 to the 14 solar masses is. Again, and that is divided by 3 times 10 to the 47 centimeter cubed, which is what 100 kiloparsecs is in volume, or in, yeah, sorry, squared, not cubed. Squared what it is in size. And so that tells us the fundamental constraint on 2 dark matter particles interacting with each other. Their cross-section divided by the mass of the particles is about 0.6 centimeters squared divided by grams. And this is around in particle physics units, 10 to the minus 24 centimeters squared per GeV. right? If the dark matter particle gets heavier, there's fewer dark matter particles. So the cross section between different particles can be higher while maintaining the same need-free path. And where are these constraints actually lie? Previously, I've just been writing the best current constraint in the bottom corner of the slide, but this is actually a bit of a debate, so it deserves its own slide. People do simulations here in cold dark matter, where cold dark matter has no interactions, or maybe some self-interacting dark matter here with 1 centimeter squared per gram as the cross section. And what you see is, as a function of time, this is a challenging problem because none of these observations, the bullet cluster, there are other clusters that are similar. They all have violent names. The musketball cluster is one, things like that. Is not necessarily in steady state. It depends on exactly when you've looked at the observation. It depends on the velocity of where things are moving at the time. So the real analyses are complicated. But self-interaction is debated. So observations of galaxy clusters by Kinematics give a constraint that is less than about some 0.1 to 0.3 grams per centimeter squared. Ren et al. Looks at simulations of steady state galaxies, which are also affected by the interactions of dark matter particles within them. And Ren et al. Observe a self-interacting cross-section of around 3 grams per centimeter squared. So that would be a detection, if it holds up, of a new property of dark matter, which is not the standard cold dark matter profile. A paper by Jesus Zavala goes back and re-examines the Ren et al. Observations and argues against them, arguing that the value is less from their observations than 1 gram per centimeter squared. Now note, they're looking at different types of systems, and it's easy to build particle physics models where these results could be velocity dependent. And I'm sure many of you here could cook up models to add some velocity dependence into this cross section. In these sorts of, in dwarf galaxies, for instance, dark matter is moving 10 kilometers per second. These clusters merged at 1,000 kilometers per second or 3,000 kilometers per second. So you can change this quite a bit. I'm going to skip the constraint of this applied to the Milky Way, and I'll leave this as a question, an open question. But calculate. Do 2 dark matter particles interact if we saturate these constraints? Good. So the last thing I want to talk about, I'm going to skip some other evidence that is particularly useful. There's good evidence for dark matter from Big Bang nucleosynthesis. This was pointed out by Martin. Big Bang nucleosynthesis basically tells us how many baryons are in. It's very sensitive to how many baryons are in the universe. And the answer is to get Big Bang nucleosynthesis right is not enough to explain the mass density of the universe. Cosmic microwave background you'll go over in detail in the cosmology lectures, but the size and the scale of this first peak in the cosmic microwave background tells us how much non-interacting matter exists in the universe. And that's good evidence for dark matter. And then there are things like the formation of structure in the universe from large-scale structure. And here are some of those simulations of large-scale structure that we talked about earlier. So the last thing I want to calculate, and showing my lack of need to actually have gone over the thermal miracle in any interaction, is what are we actually looking for when we look at dark matter in the galaxy? We're going to spend the rest of the next 2 talks talking about 2 dark matter particles come in. They interact through some cross-section, and they produce standard model particles that we can potentially observe by looking out with some telescope into the universe. And this is different, Feynman diagrams, you can run time in any direction. Indirect detection is running from top to bottom here. Start with 2 dark matter particles, you end up with 2 standard model particles you can see. Colliders, you can go the other way, start with 2 standard model particles, and they produce dark matter particles, which will escape the detector. Or you can have a dark matter particle and a standard model particle bump into each other, exchange kinetic energy, and that is what you would see at a direct detection experiment underground. So we're going to be generally looking for things that are chi-chi or chi-chi bar. If you care to track whether dark matter is its own antiparticle or not, go to some standard model particle and a standard model antiparticle. And then these are something that we can observe. And let's take one result that you're going to see in detail in about an hour, which said, or maybe a few hours. I have no idea what time it is there. So let's take the cross section to be what we call the thermal freeze-out cross section. The exact value is around 2.2 times 10 to the minus 26 centimeter to the cubed, because it's multiplied by velocity per second. This is from a paper by Steigman et al. Has the best calculation of this. Oh, it's a 2012 paper, and I forgot the archive number. I'm gonna pick for this, I'm gonna just say this is 10 to the minus 26, make things easy. And then what is the dark matter density? Well, let's just go back and talk about our totally generic model of Andromeda. The dark matter density of Andromeda, if we didn't assume any dark matter density profile, the dark matter density is just constant everywhere. 2 times 10 to the 11 solar masses divided by 4/3 pi, and our favorite number, 35 kiloparsecs cubed. This is around 2 times 10 to the 68 GeV divided by 3 times 10 to the 69 centimeter cubed. So it is around 0.1 GeV per cubic centimeter. And that is, remember, our local density was 0.3 GeV per cubic centimeter. So we're in the right ballpark here with our very stupid model for what the dark matter in this random galaxy looks like. And let's pick some standard numbers. Which will be better motivated in the next lectures. The mass of a dark matter particle, let's say, is around 100 GeV. The amount of energy you get out of an annihilation that goes into some standard model particle that you want would be the mass of 2 dark matter particles, 200 GeV. But then let's say maybe some of it you can't see, or something so you can see 10 GeV worth of it. Yeah, let's just assume 200. That's a nice number. Okay, so the amount of annihilation you get into your standard model particles is around 200. Then what is the flux of this dark matter annihilating event? So the flux is equal to the amount of energy you get per every annihilation you have times the number of annihilations. And the number of annihilations is equal to the dark matter density squared, right? Because it's the number density, because I need 2 dark matter particles to find each other. There's an annoying factor of 2 here. And that is from rho 1, rho 2 equals rho 2, rho 1. If 2 particles annihilate, they both annihilate. So you get a factor of 2 here in the dark matter mass squared. You have to deal with this cross section. How often do dark matter particles floating through space find each other? And then the volume of the system that you're trying to analyze. So if I throw this in, this is 200 GeV. This is, what did we say, 0.1 GeV per cubic centimeter squared over 2 times 100 GeV. So that cancels, very nice. This is 10 to the minus 26 centimeters cubed per second. That's the cross section. And the volume was 3 times 10 to the 69 centimeter cubed, right? And so this value happens to be, if I calculated it out based on 10, so I need to multiply by 20. It is 3 times 10 to the 39 If I calculate all my units correctly here, this GeV stays, this GeV squared cancels that GeV squared. Sorry. Centimeter to the third cancels that, and that per second. So this is 3 times 10 to the third. Let's just go to new. 3 times 10 to the 39 GeV per second. And if you convert this into astronomy units, this is about multiplied by 20 again, 5 times 10 to the 36 ergs per second, which is random astronomy unit, which is also equal to, if you want, 5 times 10 to the 29 watts. If you want to go back to physics 101 SI units. For comparison, and the moral of the end of this talk, for comparison, the luminosity of the sun, L sun, is around 3.8 times 10 to the 33 erg per second. So that's how astronomers usually quote it. And if you compare those two numbers, dark matter, so the dark matter in a galaxy, the total flux of some standard model particle, photons or something like that, that you could see from dark matter in a galaxy that's very much like the Milky Way, is about 1,000 times brighter than the sun. And you know that we can look out with observations with telescopes and see things that look like the sun in our galaxy or nearby galaxies. And so that motivates the fact that at least in this thermal WIMP scenario, with this cross-section, which will get motivated in the next lecture, you could potentially see this dark matter annihilation signal. And what's important is that this does not need to be true. This not does need to be true. Okay, this does not need to be true. The dark matter could freeze out into a configuration where it is 1,000,000 times too dim to have been seen. Or it could have freezed out from the calculation you'll see into a configuration where astrophysics is just 1,000,000,000 times brighter. Maybe it's bright enough that you would have seen the photons, but the astrophysical uncertainties will just swamp the signal because they're so much brighter. And what we'll see over the next few lectures is we're kind of in the happy or unhappy medium where neither of those things is true and dark matter is potentially detectable, but it is difficult. So to summarize for today, for thermal WIMP dark matter, or for any dark matter in particular, astrophysics tells us where to look. It tells us what the dark matter density profile is. It tells us where the dark matter density is high, and we can use the rotation curves of galaxies to potentially calculate where the dark matter density is. In thermal WIMP scenarios, it also tells us the energy scale to look at, and that's something we'll go into in a little bit more detail. But generally, if the dark matter particle is slowly moving and it, we know that the dark matter is non-relativistic, and it has a mass of a few hundred GeV or something like that for a WIMP particle, then we should look at converting its mass energy into the energy scale of those standard model particles we will look at. So we want to look for GeV scale observations. Those are gamma rays or cosmic rays or things like that. And also the last point, which we just went over, is that astrophysics tells us the signal is partially, potentially detectable. The dark matter annihilation signal should be about 1,000 times brighter than the sun for something that's the size of a galaxy like ours. That's a pretty pessimistic calculation, actually, because we didn't deal with the fact that the dark matter density is peaking near the center of the galaxy, and thus the signal is supposed to be much brighter there. But, we're in the right ballpark, and so we can potentially look out and see the signal. So in the next 2 lectures, we're going to do a crash course of high energy astrophysics and kind of all of the different considerations in, most of the light from our universe is from the galaxies and the stars and the supernova and the black holes. And so we have to know a bit about that in order to do indirect detection searches. And then we're going to look at the different things we can search for. Gamma rays, radio waves, searches for neutrinos from dark matter annihilation, and then potentially charged cosmic rays, which would be high energy electrons and positrons, protons, carbon atoms, things like that moving through the galaxy. And that's it. I see one more question in the chat, so I'll get to that. But otherwise, thank you for your attention. How well do we know the dark matter density at the center of our or any other galaxy? Once you get to the center, it's very poor. So that was the slide. Sorry for making people dizzy here. that was this slide here. These are reasonable models. And so, very close to the center of the galaxy, you can change things by a factor of 10 to the 3 or 10 to the 4 and not violate any constraints. At the position of the sun, the answer is about, the factor of 4 or so that I mentioned before. And then farther out, we know the density very well. Are there other questions? I know I went a few minutes over.
I think there's one
Yeah,
more.
more is a cusp profile. I think it goes as r to the minus 1.5 in the center. So it actually asymptotes and becomes unbound. So you have to cut that off at the center too, in order to not get an infinite annihilation rate.
Okay, so thank you. We all thank you virtually, people. And remember, we have 2 more lectures in the afternoon, and then there's a coffee break before the next lecture at 1:30 TASI time, and then the lecture itself is at 2. So I hope to see everybody there. All right, see you later.
Great. Thank you. And if people have more questions, I will try to check in on the Slack channel as well.
Good, thank you.
Any technical glitches or anything I should know for next time? Or
No, I think everything went great.
okay, good. The sidecar thing worked slightly differently than I thought it did last time I tried, but it actually was fine once I got used to the fact that it wasn't exactly what I wanted. So, so it actually worked pretty well. Okay, I will. I guess I'll be here for Martin's lecture, and then I'll see you guys tomorrow.
All right, sounds good. Thank you.